All right, in the last couple of videos, we've been working with how to get components for vectors, and we've been doing that from a two-dimensional perspective. I just want to talk briefly about direction cosines and what vectors in 3 dimensions look like. So here is some vector v, and we have it in an x, y, and z coordinate frame. And this vector, by the parallelogram rule of addition, would have 3 components associated with these 3 coordinate directions. There is a Vx component in the I, there is a Vy component in the j, and now we have a Vz component in what we call the k direction. So just like I was the unit vector for the x direction, and j was the unit vector for the y direction, we now have k as the unit vector for the z direction. That's really all those are. And if you were to add those 3 vectors up, tail to head, tail to head, tail to head, then they would give you this vector v. I'll do it here down one of the legs. So here's vx, and then if I were to add to that vy, tail to head, and then if I were to add to that vz, tail to head, then I would get the vector v. So these 3 vectors added all together would give us the vector v. Now, we could then write that vector v as vx plus vy plus vz. We could also write that as vx in the I plus vy in the j plus vz in the k, where the vx, vy, and vz are really sort of the magnitudes of the x, y, and z components. It's really just the scalar component piece that you have, and then I, j, and k are the directions. Now, we also know that we can write any vector as some magnitude times a unit vector that aims it. Now, we've already seen in our previous videos what these unit vectors look like. And so if we were to just divide both sides of this by v, then we would be left with the unit vector n. Well, then what we have over here on the other side is vx by v in the I plus vy by v in the j plus vz by v in the k. Well, vx divided by v. If you were to look at the angles made by this vector v in each of these axes, we did this previously. Let me jump back here. So when we dealt with, let's go back to the first one here. We said that v cosine of theta was vx, right here. So the angle theta measured off the x-axis, and if we take vx divided by the magnitude v, we get the cosine of that angle. Well, when I took an angle phi off of the y-axis, then I had vy divided by v was the cosine of phi. So if I took the y component over the magnitude of the total vector, then I got the cosine of the angle that the vector made with the y-axis. Just like when I took the magnitude of the x component over the x component over the magnitude of the total vector, I got the cosine of the angle between the x-axis and the vector. So what happens here is that vx by v is really the cosine of theta x, where theta x is the angle made between that vector and the x-axis. Now that's really hard to see. I don't expect you to be able to look at that and say, oh, that's 63 degrees. We don't have any numbers here. We don't know what that angle is. But it's the same principle. Theta x is the angle between the x-axis and the vector v. So if I take vx divided by that total, then I get the cosine of theta x, and this would be in the I direction. Theta y is the angle between that vector and the y component, or the y-axis. And so vy by v is actually going to be the cosine of theta y. And then if I were to take the angle theta z that the vector makes with the z-axis, then I would find that vz divided by v is also the cosine of theta z. And so that is what your unit vector looks like. Now, this is why these things I'm getting ready to write are called direction cosines, because n is cosine theta x in the I, cosine theta y in the j, cosine theta z in the k. And so if you were to plug that in up here, you say, okay, well, v is equal to some magnitude times this unit vector. Well, that's cosine theta xi plus cosine theta yj plus cosine theta zk. But that's really v times the cosine of theta xi plus v times the cosine of theta yj plus v times the cosine of theta zk. But that's really just vxi plus vyj plus vzk. And so what we call these, we don't use the cosines. That's a little bit lengthy, as you can just see. But we say, okay, well, let's call cosine theta x L. And let's call cosine theta y M. And let's call cosine theta z N. And that is the unit vector. Now, literally, the reason they chose LM and N, and it's a little bit unfortunate because, this letter N appears over here. This is the unit vector. This is the total thing. This is just cosine of theta z. So I understand if you get a little bit confused here, but we're not going to use this very often. I promise you it won't be that big of a deal. And so Lm and N become these cosines. And what we can really write is that Vx is really V times L, and Vy is really V times N, and Vz is really V times N. Be careful with that. I don't like the Lm and N personally. I would prefer to call them like Nx and Ny and Nz, and let that equal cosine theta x and cosine theta y and cosine theta z. I think that's a little bit cleaner to just subscript them. And then that way, when you write your unit vector, it looks like nx in the I plus ny in the j plus nz in the k. And nobody really thinks that much about it. But when you go with Lm and N, it can sometimes be a little bit confusing. But this is where they come from. Now, just like magnitudes for the other vectors, the magnitude of this thing is found by taking the square root of the sum of the squares. So I'll write v squared as vx squared plus vy squared plus vz squared. That is still true, just like it was earlier. What that really implies then is that L squared plus M squared plus N squared is equal to 1, but we of course know that's true because it's a unit vector, and that's actually how we got to it. All right, so don't forget your good friend Pythagoras, and honestly, you won't use this that much, so please don't let it intimidate you or frighten you or anything like that. Just a little bit of vector work. All right, I'm going to stop there. Those are direction cosines. Essentially, it's the cosine of the angle between the vector and any of the three rectangular axes. And if you take the cosine of that angle and multiply it by that vector, then you will get the component along that axis respectively. All right, that's it.